Hello again, Year 8. Welcome to Chemistry on Earth Week 5. And this topic fits in really well with the weather for this week, actually. I'm sure it's quite interesting. Amazing how these things happen. Now, your do now is on the first slide here. You have got 4 substances named: glucose, oxygen, carbon dioxide and water. And I want you to do 2 things. First of all, think about how you could group them. There's a couple of different ways you can do that, not just one answer. And secondly, using only these substances, can you write 2 word equations for different processes? Give you a hint here, because I'm feeling nice. You might want to use the cards that you had to make for your activity at the end of last week's lesson to help with this, because strangely those substances are the same. And remember, while you do this, you can pause the video. So here are the answers. First of all, you could separate the 4 substances into by the fact that oxygen is an element and the others are all compounds. That is, they contain more than 2 or more elements. Glucose contains carbon, hydrogen and oxygen. Carbon dioxide contains carbon and oxygen. Water contains hydrogen and oxygen. You could do it by their state at room temperature. So glucose can be a liquid or a solid. Glucose is a solid. Water is a liquid. Oxygen and carbon dioxide are gases. Sorry, I got a bit tongue-tied there. Right, using these to write 2 word equations, you should have the word equation for respiration, which will have oxygen and glucose as reactants. Does not matter which order they go. Carbon dioxide and water as products. Again, doesn't matter which way they can go. The other way round is photosynthesis, the process by which plants make food as producers, which start every single food chain. So, next one now. You have got 5 objectives for this week. Not too tricky. First, we're going to be explaining, so that means giving a reason, how the early atmosphere and the present atmosphere differ. You're going to evaluate where the carbon goes, find out more about that later on, understand the greenhouse effect, global warming and climate change, produce a recommendation for change. You can do this as personal work, paired work or group work. I'll explain how to do that later on. And this will be an assessed activity where you're going to submit your recommendations to me either via Teams or via email. So let's get going, lots to do after all. So the atmosphere, we know that we've got the planet Earth here and we've got different sections to it. I've put the names and picture in here to give you an idea of what goes in each section. You do not need to know the names for science. You may need to for geography, you don't for science. So the nearest bit, the troposphere, that is the level at which ordinary aeroplanes can fly. The stratosphere is the area at which military aeroplanes may fly. Mesosphere is where you will see burning bits of asteroids. That's where they start to burn up as they enter our atmosphere. Thermosphere, even higher up, is where satellites occur, and it's this bit here is meant to be the northern lights, I think. And the exosphere, there's not a lot there. Atmos is the Greek word for vapour or gas, and sphere means a globe or ball. So it's a ball of vapour or gas, and it sort of surrounds the Earth a little bit like a duvet or a blanket, I guess, but it's one that is invisible. But we know already that just because you can't see a gas doesn't mean it isn't there. And this distance up here is actually 600 kilometres. That's quite amazing. You don't need to know it, but I thought it was quite a fun fact, so I thought I'd include it. You do need to know roughly what the word means. You don't need to know all those details. This is just to explain to you. So, the early atmosphere. Earth is around 4.5 billion years old. I put it in words because that's a lot easier than writing the numbers. But if you want to write the digits, it's 3, 6, 8 zeros in that. And we get information about the earlier atmosphere from rocks. And when rocks are radioactive, you can learn from the amount of radioactivity that they contain, how long they have been around for. You'll do a lot more about radioactivity in Year 9. It's a really interesting topic to look forward to next year. Now, when the Earth formed, it was much, much hotter than it is today. It's 200 degrees back then. Now, obviously, we couldn't live in that temperature, so it's lucky for us that it's cooled down a bit. Water at this temperature is only a gas. Quite straightforward to understand that, because we know that water boils to be changed from a liquid to a gas at 100 degrees C. Any temperature above 100 and the water will be a gas. At this time there were many active volcanoes and they had lots of eruptions, and part of what they erupted was lots and lots of carbon dioxide. And there was no life on Earth at this time, so you just had lots of volcanoes, you didn't have any liquid water, you had lots of carbon dioxide as well, and it was very, very hot. Over time, the Earth cooled down. When the temperature decreased below 100 degrees C, remember that is the boiling point of water, we covered that way back at the start of this year, water vapour condensed. As the water vapour condensed, it became a liquid and it gathered on the surface of the planet and made the oceans. About 2 to 3 million years ago, so we've still got 6 zeros on there, but not the 8 that we had in the billions, the first plants appeared in the sea and they started the process of photosynthesis. And if we remember our equation for photosynthesis, we looked at it in detail last week, we looked at it in the start of this week, we will know that these plants took in carbon dioxide from the atmosphere during photosynthesis and they returned oxygen. So this led to a decrease in the amount of carbon dioxide in the atmosphere and an increase in the amount of oxygen. This can be summarised really nicely like this. We have got pie charts. Now, we know that with a pie chart, I'm sure you've looked at these in primary school, probably in maths as well, the bigger the slice of pie, the more that is contained within it. It's a different way of looking at it. If you've got 2 or 3 things, it can be easier than a bar chart. And it would be, this data could be presented as a bar chart because it is discrete data. You can't be in 2 sections. It's not continuous, it's not numbers where you can have values in between. It's discrete, it's an either or. So here, this is the early atmosphere. You can see there's 95% carbon dioxide and there's some other gases here. Today's atmosphere, we've got a lot more slices. Now, I'm not going to read all the numbers out to you because your task, first written task of this lesson, is to copy this table. So you're going to want 1, 2, 3 columns, and you're going to have the 3 different gases down the side here. Nitrogen, which is an element, but it's in double molecules, so it's 2 atoms of nitrogen joined together. Oxygen, which is an element, but it's in a double molecule. Yeah. Argon, which is an element, but it's only a single molecule. And carbon dioxide, which is also a gas, but it is a compound. It's got carbon and oxygen. You're going to put the rough percentages of those there. And then you're going to look at today's atmosphere using this chart that's underneath to put the changed percentages in here. So you'll get a number in each of those boxes, a number in each of these boxes, using the chart. You don't need to make up the numbers are on the charts. While you do this, you will need to pause the video. So, where does all that carbon go? All that carbon that was in the early atmosphere with all that carbon dioxide, it can't have just gone, because we know that the law of conservation of matter says you can't make or lose matter, you can just change its form. So it is absorbed. When it's absorbed, it's called a carbon sink. This is not like a washing up sink. It doesn't go down a plug hole. It is a sink just because it goes into a special space. We already know that lots of the carbon dioxide is taken in, is absorbed by trees during photosynthesis, and this is used to make glucose, and the glucose is stored in the wood of the tree. Some of that carbon transfers to animals when they eat the plants, because obviously they can't just eat the hydrogen or the oxygen, they will eat the mixture of all the elements within the tree. And when the animals die, it can return to the soil, and then it's available for the plants to do some more growing. Some of it will also, and some carbon will enter the soil when the leaves on trees die and fall to the ground. For most deciduous trees in this country, that happens in the autumn. For evergreen trees, leaves actually come off all year round and top up the carbon in the soil all year round. Small amounts of plant and animal waste historically became fossil fuels. That means they fell under the ground, they're put under extreme pressure, and they made either gas or petrol or coal. Some carbon dioxide can also dissolve in the oceans, and that can gather together to make rocks, which are called carbonates. And it's a bit wordy here, so I've given you an alternative version on the next slide, like this, which is a carbon cycle. It's called a cycle because it goes round. And instead of having quite so many words, it's actually got pictures. Still got a word with it, so it's still got a little bit there to remind you. So it's a combination really between a mind map and pictures. So you've got the sun shining. That helps photosynthesis occur, which takes in carbon dioxide from the atmosphere. When it decays, it goes back to the ground. So that's the leaves coming off or the tree dying. It also can go into animals when they eat it, and those animals will breathe out more carbon dioxide, so an arrow going up here. Dead animals can go down onto the ground, they can rot, where they return carbon to the plants, or they can be pressurized and make fossils and fossil fuels. Over here we've got the ocean, because we said some of the ocean will be taking up some of the carbon and making rocks called carbonates. We've also got something here on the right hand side that isn't natural. This is factories and vehicles making emissions of gases. So you will need to either copy this diagram or make your own version. The links have to be in the same places. So if you do your own version, you can't change the order and have the animals taking part in photosynthesis. That doesn't happen. We're scientists, we can only represent what's there and what we can prove. We can't guess things unless we can actually then do an investigation to prove it. Now, one part here has been added by people. I'm sure you're quite clear already what that is. And in the next couple of slides, we're going to be thinking about how does this affect the cycle and how does it affect its balance. You will need to pause the video here. Now, you will probably have heard about the greenhouse effect and the greenhouse gases. As carbon dioxide levels have risen, this has had a big effect on climate. The carbon dioxide levels have risen as we have become more industrialised, because we have burnt fossil fuels. We have burnt coal, we have burnt gas, we have burnt oil, and that has released the carbon dioxide that was stored in the fossil fuels as a carbon sink back into the atmosphere, returning it from where it was early on when we had all those volcanoes. And a theory called the greenhouse effect suggests that the layer of carbon dioxide in the atmosphere, remember we're looking at the atmosphere, the gases surrounding the planet, acts like an insulating layer around the Earth. It's a little bit like a duvet really. And this is leading the Earth to warm up, global warming. And this leads to a change in climate and rising sea levels. And sea levels rise as the ice melts, and as the sea levels rise, there is less land for people to live on, as well as changes in climate. Now, let's consider some evidence from Venus. This has all been gained by astronomers and space scientists, because nobody has actually been to Venus yet. Some probes have been close to, but no people have been there. So first of all, we've got the order of the planets. We've got the Sun here, Mercury, Venus, Earth, that's us guys, Mars, Jupiter, Saturn, Uranus and Neptune. Venus, as we can see, is near to us. It's one of our neighbours, but it's closer to the Sun than us. It's a very similar size to the Earth, and the scientists from NASA believe that once upon a time Venus had shallow oceans and some habitable land. Habitable means it could be lived on. But, there's quite a big but, so some capital letters to show it's a big but, because it is closer to the Sun, it was not able to cool down in the same way that the Earth was able to cool down over time. Because it couldn't cool down, the water that was there boiled, became a vapour, became part of the atmosphere, and the carbon dioxide levels increased. This was a greenhouse effect, same as the one that we're worried about happening on our planet with global warming. The result of the greenhouse effect on Venus is that the temperature there is 460 degrees centigrade. Now, if you can remember back on the early slides, we had the early atmosphere on Earth, the early data, and our temperature at that point was 200 degrees C, which was too hot to support life. 460 is even worse. So, what happens next? Your task, I've put a graph here. This is showing temperatures from the 1850s to 2019. That's the last whole year we've got data for. Obviously, we're only partway through this year. 1850 is the starting point because that is when something called the Industrial Revolution happened. And the Industrial Revolution was when people started to use a lot more machines to burn a lot of coal to make trains work and to have factories work, and that is when we started to produce a lot more carbon dioxide into the atmosphere. Now we know that climate change is a real problem and it needs real change in our lifetimes. Otherwise, as you can see, it does go up and down between individual years, but overall the trend, the pattern in the graph has been upwards, and it stayed very similar for a long time until just after World War II, when it started to go up considerably. And although these are small numbers, they make a big difference. Now you have to produce either a poster, a leaflet, a song, or a PowerPoint presentation to share what you've learned about climate change and what we can do about it, and at least 3 ideas for changes we can make to save not only ourselves but our planet as well. If you are bored of working on your own and you would like to work in a pair or a small group, see the next slide for information on how to do this. Now, if you would like to work with a partner or a group of up to 4 people, no more than that, otherwise it becomes unmanageable, I can set up areas on Teams where you can work on a shared document. You will have to message me because I have the admin for our class and I can set it up. So if you go to Teams, this is the Teams view, yep, you've got the general channel, you've got class notebook, which you should all have been on by now, and when you click on the little triangle, this shows 8.2 Davy, 8.3 Franklin. Looks just the same, but I couldn't show both at the same time. And there is something called collaboration space, and if you message me to say you want to be part of a group, I will set up a page for your group in the collaboration space. It's an endless page, so it's even bigger than an A3 piece of paper, and you can all work together in that space. Each of you will be able to add things, each of you will be able to take things out, but do make sure you talk to each other before you take out somebody else's work. We don't want any arguments here. I just thought it'd be a nice thing to do for a change. Okay, so that's an option you've got there if you can get on Teams. If you've got a problem getting onto Teams, message me and I will help you. So, your objectives. At the beginning we said, explain how the early atmosphere and the present atmosphere are different. That was the activity with your pie chart. Evaluate where the carbon goes. That was your carbon cycle. Understand the greenhouse effect, global warming, climate change. Produce a recommendation. These last 2 are the bits that are here in red. Submit your recommendations on Teams or via email. This will be a whole class feedback activity, which means there'll be an exciting video to go with it next week, but also you can be recognised in that video and have a quote shared with everybody. If you've got any questions, you know what to do. Otherwise, have a great week. Look forward to hearing from people that want to collaborate together, and hopefully see you or speak to you soon. Take care, Year 8. Bye for now.